In this session, so we are going to see how analog signals can be converted into digital. To convert any analog signal to digital, we have some steps. So what are those steps are sampling, quantization and encoding. So now let us look into sampling. So sampling means it is nothing but converting your analog signal into discrete time signal. So if there is an analog signal like this, so you have to discretize. Discretize means at regular intervals of time. I will take the signal bigger. So at regular intervals of time, so you are picking the samples. So you are picking the samples like this. So where the interval between the two samples should be constant, regular intervals of time. So you are going to pick the samples. So this process of converting your analog signal so that you get only discretized signals like this. Okay, so this is discrete signals with respect to time. So therefore, this process of converting your continuous signal into discrete signals, so by measuring the signals at regular intervals or periodic intervals of time. So, and one more important thing that we need to concentrate is the timing interval Ts. What should be the value of Ts? That is very important to decide what should be the value of Ts, so that you can reconstruct the receiver. So we are using sampling theorem. So that is what I said. So sampling rate is very important. Okay, so that can be decided by using sampling theorem. So let us directly state what is sampling theorem and then let us prove that. Okay, first coming to the statement. So if you consider any signal which is of infinite, it can range from minus infinity to plus infinity. Any signal which is having finite energy, the energy of the signal should be finite, measurable. Okay, so this should be measurable. So energy should be measurable. So if a finite energy signal g of t contains no frequencies higher than WHz, no frequencies higher than WHz means, so it is a low pass signals. Okay, band limited signals, band limited to WHz. So if you consider any signal which is having finite energy and no frequencies higher than WHz, then such type of signals can be completely recovered from its samples, from its ordinates at a sequence points. If the spacing between them, I said no, these are the samples, whereas the spacing between them, whatever the spacing that you should choose, it should be 1 by 2 W, or so if I choose the sampling rate, then it is 2W. So if your sampling frequency is greater than or equals to 2W, okay, then only you can completely recover your signals from its samples. This is what the sampling theorem states. Now let us prove this sampling theorem. So while proving this, so I am going to do it with two different steps. One is, first let us represent this analog signal that what we consider in samples. These analog signals are sampled first. Okay, second thing, so from these samples I have to get back the original signal, that is reconstruction. So these two steps, with the help of these two steps, so I am going to prove the sampling theorem. So first let us consider analog signal g of t as indicated in the statement, which is having finite energy and the frequency is not more than WHz. Okay, now I want to get the sampled wave. How do you get the sampled wave is, so we need to pick the samples at regular intervals of time. Regular means, so at interval time equals to 0, then at time t equals to Ts, at time t equals to 2 Ts. This is periodic instance, 3 Ts and so on. Similarly, it can be minus Ts, minus 2 Ts at regular intervals of time I am picking the samples, so that you get the sampled wave like this. So that is what it is indicated. Let us consider the sample values of g of t at every instance shown like this. Then the sampled signal can be represented as g of nts, where n can take any values like this, 0, plus ts, plus 2ts, and so on. So where ts is, this is the time interval between the two samples, or it is also called sampling period, where sampling rate or sampling frequency is inverse of time, that is fs is equals to 1 by ts. Now all the samples g of nts are called the samples of g of t. So to obtain this sampled wave, what we do is, so we multiply your analog signal with a shifted version of delta function, that is delta of t minus nts. When n is equals to 0, this equation becomes delta of t, because this term becomes 0. So delta of t means at t equals to 0, at this point, so you get a delta function. Okay, so and next, when n is equals to 1, this becomes delta of t minus ts. At t equals to ts, you get a delta function. Similarly, at 2ts, 3ts. Now I can multiply. So this analog signal are the samples of analog signal, okay, with delta function, so you get this sampled wave. Therefore, so I can write mathematically this equation as g delta of t, the sampled signal, g delta of t can be written as summation n ranging from minus infinity to plus infinity, all the samples of g of t, that is at 0, plus 2ts, 3ts, 4ts, etc. So g of nts into Dirac delta function, this is Dirac delta function. If you multiply these two, you get the sampled signal, okay, where either I can write g of nts, or if you add all the samples of g of nts, so this is nothing but g of t. So I can write g delta of t is just g of t into delta of t minus nts. Therefore, so I will write it as, so g of nts, or I can write it as g of t. Okay, all the samples together, we call it as a analog signal g of t. So this can be now modified. So equation 1 was, so g delta of t equals to summation g of nts was there. So in place of g of nts, so equation 2 I am substituting here. So it becomes g of t into delta of t minus nts. So this is your analog signal, and this is your Dirac delta function, where this can be represented as, so delta of t minus nts, so just can be represented as delta ts of t. I will just replace this summation delta of t minus nts with delta, this is just a notation, delta ts of t. Therefore, the above equation, equation 3, can be represented as like this, that is left hand side is g delta of t and right hand side g of t as it is, whereas Dirac delta function I have represented as delta ts of t. It is a multiplication between these two. Therefore, it looks like a product modulator. This is your input signal, this is your carrier wave. If you take a multiplication, product modulation, then you get the modulated wave. Same way, so but here you are getting impulse modulator. The signals are impulse in nature, because the duration of the pulses is 0. You are getting impulses. There is no pulse width like this, right? So therefore they are impulse modulator. Now this is with respect to time domain. This is with respect to time domain. But to understand better, so let us represent the same signal in frequency domain. So if we represent this in frequency domain, so we need to go for the Fourier transformation. So we know that g of t, if you take the Fourier transform, I can write it as g of f, Similarly, g delta of t, I can write it as g delta of f, and delta of t minus nts, if I take the Fourier transform, so I get fs constant into summation n ranging from minus infinity to plus infinity delta of f minus nfs. This is a Fourier transform of Dirac delta function. So therefore I can write, so g delta of f, g delta of t can be written as g delta of f, and see in the time domain it was multiplication. So if you take a conversion time to frequency, it becomes a convolution. Therefore dot is replaced with star, and so Fourier transform of g of t is g of f. I have written it g of f. Fourier transform of delta of t minus is, so this. So take the convolution, and to simplify this is constant, I will retain as it is. I can bring this g of f inside the summation. So it becomes fs into summation m ranging from minus infinity to plus infinity, so on. So now if you understand this, so g of f multiplied with or convolved with delta of f minus mfs. Okay. Now if you multiply any function with delta of f, means it is a unity function. Okay, it is whose amplitude is always 1. So 1 into g of f, you will get g of f only, but where? At every mfs. Therefore, so this convolution I can write it as g of f minus nfs. This is the frequency domain representation of the sampled wave g delta of f. This can be understood, the equation can be understood if I represent in the form of spectrum. Let us represent that. I will take the same equation, that is g delta of f equals to fs into g of f minus nfs. Now, so where n is so and so, it can take all the values of that 0 plus or minus fs, which means that, so this g of f is shifted at every nfs. Suppose if n equals to 0, it is just g of f. When n is equals to 1, it is g of f minus fs. That means at f is equals to fs, you will have a g function, input signal. Okay. So let us understand by plotting the spectrum. So that is, if this is the case, g of f, let me assume this is the spectrum of g of f. Now when n is equals to 0, as I said, so it will be just g of f. The sampled wave also you get g of f, same shaded spectrum. Now when n is equals to 1, then it becomes g of f minus nfs, 1fs. That means at fs, at f is equals to fs, that means this point, at f is equals to fs, you have g of f, this function. So this function you are going to bring it here. So this 0 will come and sit in fs place. Understand? So similarly, so take different values of n, so that this spectrum will be shifted. How you get the exactly aligned with WS? We have chosen fs equals to 2w. I have chosen the sampling frequency fs is equal to exactly 2w. This is 1w, this is another 1w, totally 2w from here to here, fs. Okay. So we have chosen fs is 2w. So let us understand this better, choosing fs less than 2w. If you choose fs less than 2w, this will be the spectrum. Suppose if I take, this is your spectrum of the message signal. So here I have taken so linear. So here practically, so you may not get such a linear. So you slightly it may vary. This is the spectrum of g of f. Now what will be the sampled wave? When n equals to 0, this is the spectrum, same as your g of f. When n equals to 1, this is the spectrum. When n equals to 2, this is the spectrum. When n is equals to minus 1, this is the spectrum. So if I take the overall spectrum of this, see, you can observe that there is a overlap here, correct? So you can see that there is a overlap, all these cases. So if you summarize this and take the spectrum, so this solid line, so you get a spectrum like this, which is not same as your g of f, which means that if we choose the sampling rate less than 2w, so you cannot reconstruct this. this effect of overlapping the spectrum, we call it as aliasing effect, which means that the spectrums will be overlap and you cannot get back the original signal. So the other case, choosing Fs is more than 2W. So if you choose Fs more than 2W, so you can observe this is the spectrum. So this is your G of f. So when n equals to 0, you get this. When n is equals to 1, you get this. That means you are shifting at Fs, where Fs is greater than 2W. So when you choose greater than 2W, you can see that there is a gap between the spectrums. So there is no overlapping of the spectrum. So in the receiver, I can simply use a filter and get back this signal sidebands, so that this is same as your message signal. So Fs should be equal or more than, then only you can reconstruct. So in this case, when Fs is less than that, so you cannot reconstruct your signal. This concept is called aliasing. So you can stop here saying that we have justified with the help of frequency domain. But if you want to show mathematically how you can reconstruct your signal, okay, you can still continue with the derivation. That is, so delta can be represented in exponential form, exponential of minus j 2 pi nfsts. Okay, so I'm substituting in equation 1. What was equation 1? G delta of f is equals to summation g of nts into delta function was there. This delta function is replaced by exponential. Now with the help of this, so I am going to reconstruct the signal. So reconstruction of signal, again we had 3 conditions, but I am choosing the ideal condition, that is Fs equals to 2W. When Fs is 2W, Ts is 1 by 2W, as we know. Okay, so now therefore equation 6, that is the previous equation, which is in terms of exponential, can be represented as G delta of f becomes G of nts. What is Ts? 1 by 2W. Okay, into exponential of, so just substitute that equation. Okay, substitute wherever Ts is there, you substitute 1 by 2W, you get equation 7. Okay, so now, so if you look into this equation, so these two, so G delta of f can be written as, so here, so you get Fs into G of f. How you got this equation is from previous slide. So that is, the sampled signal is Fs into the input signal. Okay, the frequency domain representation of sampled wave. Okay, now, so I want G of f, right? So substituting Fs equals to 2W, get G of f. What is G of f? It is 1 by 2W. You send 2W to the other side, it becomes 1 by 2W into G delta of f. So now G of f is equals to 1 by 2W is constant. In place of G delta of f, so you can substitute equation 7. Okay, so that you get this equation. Similarly, taking the inverse Fourier transform of G of f, because this is the reconstructed wave in terms of Fourier frequency domain, but still we cannot understand whether we have reconstructed or not. Therefore, let us take the inverse Fourier transform, so that I get the time domain equation. So if you get the time domain equation, that is for inverse Fourier transform formula, G of t is integral ranging from minus infinity to plus infinity, the Fourier transform signal G of f into exponential of that. Okay, so substitute what is the value of G of f from equation 9. Okay, so you get this expression. Anyhow, this exponential is there as it is, just G of f I have replaced here. Now, so simplifying this by interchanging the summation and integration, so you get this, so because it is in the form of e to the power a into e to the power b. Okay, so e to the power a plus b, since you have negative sign here, so negative sign will also come here. Okay, keep on simplifying this. So after integration, e to the power ax, so e to the power ax by a. So simplify that, apply the limits. Okay, minus w plus w, so you get this. So after substitution of that, so you get, So in the form of sine, e to the power j theta plus e to the power j theta minus e to the power minus j theta divided by 2. So you will get it as sine. Okay, so if you simplify that, so you will get it in the form of sine pi x. It is in the form of sine pi x divided by pi x. So this formula is sinc x. Okay, therefore sine pi x by pi x can be written as sinc function. So what is this sinc function is, if you have samples like this, okay, so if you apply sinc function, suppose if I say this is the first sample, I multiply with the sinc function. Sinc function is, so will respond to like this, so it rolls up to 0, maximum amplitude at that frequency, and it rolls up to 0. Similarly, sinc function for this, maximum amplitude to this, and it rolls up to 0. So if you add these together, so you get a sample like this. That means if the two samples are known, the in between values are calculated with the help of signal, so that you get the original signal. Okay, that is continuous signal, and this continuous signal what we get should be same as the original message signal that what we have taken. So this sinc function is also called interpolation formula. It is used to interpolation formula. That means if two boundaries are known, in between samples can be calculated with the help of this, so that you can get back your time domain waveform. Okay, so with this we have reconstructed the sampled wave. So this is a proof for sampling theorem. So thank you for watching the video. So if you have any queries, you can put in the comment box. So kindly subscribe. Thank you very much.